Hi, I'm Roland Maio, and today with Monachou and Patro, we will present joint work with Jesse Finocchiaro, Raghavan, Stoica, and Tsirtsis on bridging machine learning and mechanism design towards algorithmic fairness. Decision-making is increasingly supported by or relegated to algorithms. In online advertising, algorithms determine the ads a website visitor sees in fractions of a second. In labor markets, algorithms suggest professional connections and connect workers and companies. In education, algorithms are used in many ways, including to predict the potential of applicants to a school. A critical feature of many of these applications is that they have both mechanism design aspects, such as involving markets and resource allocation, and machine learning aspects, applying machine learning tools to problems of prediction and decision-making under uncertainty. Since algorithms are not perfect, the scope and import of these applications has prompted significant scrutiny of the underlying algorithms, often surfacing concerns that the algorithms may be unfairly biased. Take, for example, this recent news story from the United Kingdom. To determine each student's results, the UK decided to use an algorithm that looked at their mock exam results, as well as their school's track record in the exams. As we read in the article, approximately 39% of A-level results were downgraded by the algorithm, and the model ended up favoring students from private schools and affluent areas, leaving high achievers from free state schools disproportionately affected. Fairness of decision-making algorithms, markets, and resource allocating systems is a question that has been asked in various forms and from very different perspectives by both computer scientists and economists working on machine learning and mechanism design. Specifically, they ask, are common decision-making and resource allocating systems fair, or do they reproduce or even amplify discrimination patterns from society? In this paper, we look at fairness considerations in both fields and argue that it is necessary but not sufficient to consider machine learning and mechanism design in conjunction to one another. We believe that taking each field in isolation will ultimately lead to gaps in our broader understanding of decision-making systems and the impact these systems have on society. Of course, these are not the only fields that are important to study socio-technical systems in a broad context, so this is why considering only machine learning and mechanism design is not sufficient, and more interdisciplinary research is needed as well. To summarize our goals, we aim to identify the gaps between how machine learning and mechanism design reason about fairness, detail concrete lessons each field can learn from the other, and help build a lingua franca of fairness in joint machine learning and mechanism design systems. Okay, so we've motivated the problem and broadly located our work in the field of algorithmic fairness. Now we'll try to understand how machine learning and mechanism design define and approach fairness, and afterwards we will talk about lessons that are already learned or should be learned from the common study of the two fields. The most important and possibly most challenging task in algorithmic fairness is to define fairness in the first place. Ronald Dworkin, a famous jurist and political philosopher, couldn't have put it better when he said, "People who praise fairness or disparage fairness disagree about what they are praising or disparaging." There's absolutely no consensus on what fairness means, even within the same field. Yet, in spite of these disagreements, mechanism design and machine learning have each successfully developed frameworks for defining fairness that are largely shaped by their respective foci and technical methodologies. Let's review some of the most important fairness definitions. First, in machine learning, fairness is typically defined as a constraint on an optimization problem. Thus, machine learning algorithms typically optimize some other metric, for example, classification accuracy, and fairness restricts the set of feasible solutions. The setting of binary classification is the most well-studied in machine learning. There's a data set with labeled training examples. The ith training example is a pair xi, yi, where xi is a feature vector denoting information about the ith training example, such as a school transcript, and yi is a class label, often -1 or +1. The goal is to build a good classifier, often meaning highly accurate, As you can see here in the picture, the classifier is the line that separates the circles from each other, and a good classifier separates the classes well between the two different colors. In fair machine learning, we ask that in addition to being highly accurate, the classifier also be fair. Binary classifiers are also highly relevant to the study of algorithmic fairness because they can often be viewed as making decisions, where, for example, a prediction of -1 operationally means reject, and a prediction of +1 operationally means accept. So what do fairness constraints look like? We have two main categories, individual fairness and group fairness. There are many concepts for individual fairness. They all have in common that an algorithm must be fair with respect to every individual. One of the first and most common one is fairness through awareness, which requires that similar individuals be treated similarly with respect to the machine learning predictions. In contrast, group fairness definitions de-emphasize individual level treatment and emphasize treatment aggregated at the level of the groups to which individuals belong. They require that an algorithm must be fair with respect to its average treatment of members of different groups, which are typically based on things like race, gender, and ethnicity. One of the first and most common is demographic parity, which requires that the probability an individual is assigned a certain outcome is independent of their group membership.
Moving next to mechanism design, we have a wide range of definitions. We definitely have some fairness definitions from social choice theory, but I will skip them since they have been used mostly in fair division and voting problems and are not the main focus of our paper. In any case, our paper mostly focused on the first two parts here: economic theories of discrimination and utilitarianism and welfare economics. The economics literature has developed two main theories of discrimination. Their key difference is the effect of information. We have taste-based discrimination, which arises due to pure preferences and persists even with perfect information. It is based on the principle that decision makers derive higher utility from certain social groups than others. We also have belief-based discrimination. Within this theory, the most well-known type is statistical discrimination, which arises due to imperfect information. This can be particularly useful for machine learning models, since it assumes that the true attribute of an individual is observed through a proxy, like noisy features or signals. Of course, we have another well-known objective, social welfare. Social welfare can take several forms, but in its utilitarian form, it is simply the sum of individual utilities or happiness over an outcome. A common objective in mechanism design models is to design a system so that the social welfare is maximized, potentially given certain constraints. So why social welfare is even a fairness notion? Part of the reason comes from the historical context of welfare economics and its connection to the philosophical system of utilitarianism. But more practically, we see how this notion can capture fairness. For example, we could assign appropriately defined weights to different individuals' utilities and compare the welfare across different groups. Next, we move to the main part of our paper, where we talk about lessons that are already learned or should be learned from the common study of the two fields. There are 5 lessons. The first lesson is about the relation between fairness and welfare. After 10 different definitions in fair machine learning, where all have problems, a growing line of work has asked the following question: should welfare be the primary metric for the effectiveness of a social policy? There are some preliminary results that show that the answer is probably yes. For example, we have a couple of papers showing that adding group parity constraints can lead to a welfare decrease for every group. Another reason in favor of using welfare is that fairness notions in machine learning lack expressivity since they fail to acknowledge inequality within groups and heterogeneity of preferences over outcomes. On the other hand, our paper argues that using welfare is not panacea. Many practical questions and concerns arise. For example, whose utilities should we maximize? How much weight should each individual be assigned and why? Should the average utilities of all groups be the same, or should each group contribute to the total welfare proportionally to its size in society? In the end, we argue that while there may be no universal notion of fairness that adequately captures society's beliefs about whose welfare to prioritize, mechanical design provides the tools to begin to study these welfare trade-offs in a way that machine learning has yet to fully reckon with. The second lesson concerns long-term effects. The first point we make here is that dynamic effects over time are crucial, and if neglected, they can rather worsen than improve the existing discrimination. We see this failure to capture long-term fairness even in two-stage models. For example, with respect to the effect that the fairness policy has on an evolving population or a pipeline of decisions. Second, even if we try to account for its long-term effects, the type and complexity of interventions may vary significantly. Some short-term interventions may be sufficient in certain cases, but in the general case, the optimal policy gets quite complex. A classic example is affirmative action. For example, it is not clear whether the positive effect of affirmative action will continue after a policy is lifted in certain settings. Finally, a factor that we consider very important is the dynamic effects of human or social bias and its interplay with algorithmic bias. This is especially relevant for settings such as online labor markets that utilize user reviews to make decisions and as a result combine human and algorithmic decision systems.
Here in the third lesson, we talk about strategic agents. As machine learning algorithms are made to be more and more transparent in settings like hiring, loan approval, school or college admissions, the individuals who are being classified or scored are more than ever capable of gaming the decision-making systems by strategically altering their features. Recent works on classification in such strategic settings raise several fairness concerns. The vulnerability of these systems to strategic manipulations urges for incentive-aware design of machine learning algorithms. However, a paper by Millie et al. Shows that protecting the decision maker from feature modification could lead to social burden on different groups of individuals, especially the individuals from historically marginalized groups. This is because preventing feature alteration could also prevent true investment of effort for improvement. Let us consider a simple example of admitting graduate students solely based on an observable feature like GPA. Here, two students having same GPA could also be a case of two seemingly similar individuals with dissimilar effort profiles. This could be due to the dissimilarities in their ethical, cultural, or socioeconomic backgrounds. Treating these two individuals similarly could undermine the significant amount of effort put in by the individual from a marginalized group. So, in order to make decision making systems transparent and fair, there is a need for strategy proofness, which captures the complex relationship between features and individual qualifications. Our fourth lesson focuses on uncertainty. As mechanism design often deals with preferences and utilities, it assumes that individual preferences are somehow known to the central decision maker. However, in more complex settings like online advertisement and labor markets, the preferences are unknown a priori and must be estimated in practice. This involves uncertainty. Here, the fairness notions from machine learning can help deal with fairness concerns relating to this uncertainty and estimation errors in these complex systems. Moreover, uncertainty can also manifest with respect to outcomes, not just preferences. For example, mechanism design models often assume the structure between inputs and outcomes is known, even though it is probabilistic. But in complex systems, there is always a lack of ground truth on the outcomes. which even complicates the analysis of a mechanism. However, it is precisely the place for machine learning techniques, as fair machine learning literature can greatly help in defining and measuring disparities coming out of these learning or estimation processes. More importantly, the group fairness notions from machine learning literature can also help and can also be used as a diagnostic tool for potential harms originating from group level disparities in outcome. The final lesson is on human perceptions of fairness, which is at the intersection of machine learning, mechanism design, and other fields like human computer interaction. A paper by Kleinberg et al. In 2017 shows that it may be impossible to simultaneously satisfy multiple fairness definitions. Given this result, real world decision making systems must be restricted to only selected principles of fairness. This poses a very challenging questions on how to select right principles of fairness, especially in applications like criminal justice, finance and lending, and self-driving cars. Given the applications of these systems and their potential for significant societal harm, it is essential for the chosen principles to be socially acceptable. Towards this goal, one must understand how people assess fairness and how to account for all voices while selecting the fairness principles and designs. This requires a socio-technical participatory approach to fairness, giving rise to three major questions. First, whose fairness perception should be captured in the process? Should it be the lay humans, domain experts, or just the primary stakeholders? Secondly, what sort of options or information should be made available to the participants? Studies targeting this question reveal the importance of model explainability and transparency in fairness perceptions. Finally, how should we aggregate the participants' preferences? While voting theory from mechanism design can help answer the question on preference aggregation, insights from socio-technical and sociological studies can substantially help in building good participatory designs for fairness. To conclude, in this paper, we have shown some open questions at the intersection of machine learning and mechanism design. We also argued that it is necessary to develop a common framework of fairness by identifying different knowledge gaps and lessons and ultimately bridging the two fields towards algorithmic fairness. It is worth noting that making the system fair from a technical perspective does not mean that the whole system is perfect. So, the research on algorithmic fairness needs more interdisciplinary effort even beyond machine learning and mechanism design. Our paper is available at the highlighted link. Thank you for attending.